Record. All right. So when we talk about ions, does anyone want to take a guess as to what ion means?
I want to say it means charge, but that's probably.
Whoa. What was that again?
I want to say it means charge.
Yes. Ions are charged particles.
I believe that says long.
Nope. It's ions. Charged particles. And more specifically, atoms. Okay? So an ion is a charged atom. So how do we achieve a charge in an atom? Yeah. Yes, mismatched. I couldn't have said it better myself. Mismatched number of protons and electrons. Okay? So when we talk about ions, you know that they are charged. We'll throw that in there to make it nice and pretty. Thinking, still thinking. So a mismatched number of protons and electrons. Why would that give us a charge? If the number of electrons is not equal to the number of protons, why would that give us a charge? Hannah? Right. Right. Oh, that's an underscore. So when we talk about protons and electrons, we need to remember that they have charges, right? Proton has a positive charge, electron has a negative charge. When an atom has the same number of protons and electrons, that means that it has a neutral charge. It doesn't have any charge. But if the number is different, then it is a net charge of positive or negative. If you have more electrons than protons, you have a negative charge. If you have more protons than electrons, you have a positive charge. Okay? More protons is positive. More electrons is negative.
I was thinking about that. It kind of makes me upset. For the sole reason that electrons sound like they should have a charge.
They do. They do have a charge. So electricity, so electrons are named after electricity. And when we get to metals, we will talk about how electrons make electricity work.
Yeah, but like, it's just, they should have a positive charge.
Yeah, well, all right. So ions, charged particles, more specifically atoms, okay? So when we talk about ions, we use specific terms, okay? We use the term anion and cation. An anion, and that gets a little bit confusing, an anion has a negative charge. Okay? Cations are positive. Okay? And I know that looks like cation because English is stupid. Cation. By the way, whoever made the rule that T-I-O-N makes a shun sound needs to be fired. Okay, like, so it comes from the Latin. It comes from Latin stuff. So for instance, like if you do in Spanish, right? Seleccione, right? That's like, then that was selection. That's a really terrible. Selezione, that'd be like Italian. In Portuguese, it's seleção. It's a sound that we don't make in English. Oh. But English, we're like, no, this is going to be a shun sound.
Yeah, we basically took everything from different languages and made it.
Yeah, English is a mutt. It is a combination of several different languages. Germanic, Latin, a little bit of old Celtic, and so forth. Anyway, so cations are positive, anions are negative. The way that I remember this is cats are positive.
Very good. That is very good.
Okay. Happy cat. Yay. All right. Cats are positive. Not really though. I mean, they're always super grumpy and obnoxious, but.
Yeah, right, okay.
Okay. So anions are negatively charged ions. Cations are positively charged ions. So let's do a couple of examples. All right. So on your periodic tables, let's look at. Let's look at rubidium. Rubidium is Rb, it's number 37. Rb, that is 37. Okay. So rubidium is atomic number 37. How many protons does that have? No. 37 protons. Remember that the atomic number is always the same as the number of protons. If this is an anion, with a charge of 2, anion with a charge of 2, how many electrons does it have? What was that, Hannah? 39. So if this is an anion, with a charge of 2, that means that we have 39 electrons. Do we see how that makes sense? Because anions are negatively charged, and therefore we have more electrons than we have protons, and it is an anion with a charge of 2.
If it was a charge of 3, it would be 40.
And if it was an anion with a charge of 3, it would be 40. Yes. So let's look at another example. All right. So we have an element, and we know the number of electrons. We know that this element has 44 electrons. Okay? 44 electrons, and this is a cation. Guys, I have gotten better at writing with this, I will say. A cation with a charge of 1. Okay? So this is an element that we don't know the element, and it has 44 electrons. It is a cation with a charge of 1. What element is this? Hunter? It is rhodium. Okay? Rhodium, which is RH. Why do we know that, Hunter?
Because the charge
Because, yes, because we have 45. If this is a cation with a charge of 1 and we had 44 electrons, that means that we have 45 protons. And 45 protons means that it is element number 45. You see how that works? All right, let's do one more example for ions. Okay. So we have, let's go with chromium. Chromium is element number 24. 24. If this atom has 22 electrons, what is the charge and what type of ion is it? What is the charge and what type of ion is it? Hunter.
Anion.
Okay, so you've got a charge of 2. You said it was an anion, yeah?
Yes.
Okay. Why is Hunter half right here?
Because
it is a cation.
Oh, it's a cation
Because we have more protons. Okay? A cation with a charge of 2 because we have more protons, right? We have more protons. 24 is greater than 22. Therefore, we have a positive charge. So you were half right there, Hunter. We had a charge of 2. Well, you got to remember which direction we're going. Okay? Questions on ions, cations, anions. Has anyone heard the term cathode and anode before? No? Yes? A couple of you maybe? Cathodes and anodes are also in batteries. A cathode is the positively charged part of the battery, and the anode is the negatively charged part of the battery. Whoa, it's like, it like makes sense. Okay? All right, so that is ions. Now we need to talk about atomic radius. Okay, let's throw in a picture here. There's our cats. Oh, is the computer gonna just die now, or what's going on? Okay. Do I have too many tabs open? Is my computer struggling? Let's go with this one, just because it's the second one available. So now we need to talk about atomic radius. And when we look at a picture like this, how accurate do you think that is for how an atom actually looks?
I think it's a lot bigger.
I think it's a lot. Okay, yeah, that's a good point. It's a lot bigger than an atom. I do not know what is going on here. We've got the nucleus here, and then we have these big things going on the outside, and then we have a small thing. Like, what in the world? This is like not what an atom looks like at all. Real atoms are kind of messy. They're like, so here's the nucleus. And the traditional model is where you have like 6 things that go around like this, right? Oh gosh. Oh yeah, so pretty. Right? That is in no way accurate, okay? That is in no way accurate. Okay, actual atoms, we're gonna get them all, Gotta catch them all. All right, actual atoms look like this, okay? You have a nucleus in the center, and then the electrons do this thing where they're like, and they're all over the place, okay? And, okay, you have what is called an electron cloud around the nucleus, all right? The atomic radius of an atom, atomic radius, just from hearing that, you should probably be able to understand the basic idea of what it is. What would you guess the atomic radius would be? Go, Davis. What would you guess the atomic radius is? So first of all, what is a radius?
The radius is half of the diameter.
It is half the diameter, but what is the diameter?
The diameter is the measurement of the inside of a circle.
Okay, the measurement of the inside of the circle. So when we look at a circle, we have the radius is this distance right here. Okay, little r. Okay, the radius is the distance between. Can I not? No. I want the nucleus. No, you're good. So the atomic radius is the distance from the nucleus to the outermost electron shell. So electrons go around the nucleus in shells, all right? We'll talk about that later, but what you need to know right now is that the atomic radius is the distance between the center of the nucleus to the outermost electron. And for atoms, this is actually quite a big difference, all right? So for instance, if you had an atom that was the size of a football field or a football stadium, or pick your favorite sport, of a large stadium, the nucleus would be the size of a basketball in the center of the stadium. Most of that area is just emptiness. Okay? Most of matter in the universe, so most of what makes you is actually just empty space in between the nucleus and the electrons in your atoms. Okay? Yeah, you're empty and hollow inside. I know that feeling every day of my life. Okay. And if you recall in discussing in my other classes that you actually never touch anything because the atoms in your fingers never touch, never make contact with anything. Okay?
I mean, then how can we figure that?
That's the repulsive energy between the electrons in the atoms. So they're pushing against each other, kind of like magnets push against each other, but they don't actually touch. So I don't actually touch this table right now. I don't touch the computer. What is happening is the electrons in the outermost shells of the atoms in my fingers are pushing against the electrons in the outermost shells in the atoms of the table. No, you're not floating. You are repelling electromagnetically. Okay?
How much force do we need to actually touch atoms?
To actually touch atoms, you need a lot of force. In fact, you need so much force that you would create nuclear fusion, at which point your body would explode. And when I say explode, I mean make a crater about the size of the state of Utah explode.
Which is not cool.
Okay. So when we look at the atomic radius, this is measured measured in a very small thing, which is a picometer. Okay? Picometers. So remember when we talked about SI units? You have meter, right? And then you go smaller than meters. You have centimeters. You have millimeters. And then you have micrometers. And then under that, you have nanometers. And then under that, you have femtometers. And then below that, you have picometers. Picometers are 1/1,000,000,000th of a meter.
Oh, that is so small. That is so small.
Okay? Picometers are unbelievably small. Atoms are tiny. Okay? Even the biggest ones. And we're going to talk about the differences in atomic radius of atoms. So if we go to our handy dandy ptable.com, ptable.com. So we have hydrogen up here, we have helium, right? And then we have some of these atoms with more protons in the nucleus. We have tin down here, antimony, right? Silver, palladium, copper, strontium. Strontium is a pretty cool name. I think that probably the coolest of them is titanium, though, let's be honest. I mean, named after the Titans. That's pretty sweet. Okay. So when we talk about atomic radius, there is a trend on our periodic table. There is a trend in our periodic table. And I'm going to draw this for you, and because, you know, I love drawing so much, and you're all just really waiting for my beautiful drawings, we're going to draw a periodic table here. Okay, beautiful. Okay, we've got a periodic table. It is not accurate, but when we talk about atomic radius, so if you have more protons, if you have more stuff in your atom, you would expect the atom to get larger, yes? And that is true. As you move down the periodic table, you get larger. Okay? As you move down, you get larger, but there's also some other things at work here. Okay? So I want you to look at your periodic table, and we'll talk about this in greater detail later, but the rows here, so remember that rows are side to side and columns are up and down. The rows indicate the number of shells of electrons. Okay? So for instance, sodium has the same number of electron shells as phosphorus because they are in the same row. Potassium has the same number of electron shells as gallium because they are in the same row. Okay? Why is this important? Because if you have the same number of shells, but more protons in the nucleus, the protons pull on the electrons more powerfully. So going back here, so this way down means so the arrows indicate larger atoms. Okay? Larger atoms. And I'm just going to abbreviate it as A(r), atomic radius. Okay? Larger atomic radius as we go down, because obviously you have small numbers up here, you have big numbers here, right? Obviously beryllium has fewer protons than barium, right? However, when you move to the left in the same row, When you move to the left in the same row, that also means that the atoms get larger. The reason is because, again, so let's look at potassium, okay? Potassium has 19 protons, and it has the same number of electron shells. An electron shell is kind of like an orbit around the nucleus, okay? In this case, potassium has 4 shells. 1, 2, 3, 4. Okay? It has 4 shells. Well, potassium has fewer protons than germanium, which is over here, number 32. Because of the additional protons, germanium actually pulls its electrons closer to the nucleus. Does that make sense? So there's a trend, okay? There's a trend. The smallest is helium. Smallest atom in the periodic table is helium. And the largest atom in the periodic table is francium. And so we see this trend of down and to the left, you have larger atoms, okay? So let's see here. Without looking at anything, knowing the trend, let's compare sodium. Would sodium have a larger or smaller atomic radius than beryllium? Would sodium have a larger or smaller atomic radius than beryllium? Beryllium is here, number 4. And sodium is here, number 11. Is sodium larger or smaller? Than beryllium. Sodium and beryllium, 4 and 11. 4 and 11. So sodium is bigger. Why is sodium bigger? It is more to the left and it is more down. So when we look at this, we can actually look right here. If we click on beryllium, radius. Beryllium has an atomic radius of 112 picometers. And sodium has a radius of 190 picometers. So it is much bigger. Okay? By a full 78 picometers. Okay? All right, what about calcium, number 20? Calcium and zinc. Will calcium be larger or smaller than zinc? Zinc is 30, Zn. Calcium is 20. So 20 and 30. Calcium will be what? Bigger, right? So because calcium doesn't have quite the pull as zinc. They have the same number of electron shells. So if we look at calcium here, we can see that the radius is 194 and zinc has a radius of 142. Do we see how this works? The atomic radius is, and I'm not going to get into too much of the reasoning as to why the protons pull on the electrons more. That has to do with something called Coulomb's law. And if you choose to take AP chemistry, you'll learn about that. But we're just going to kind of generalize this rule right now. Okay? Questions on any of this? Atomic radius. Pretty straightforward. Okay? So if you don't have this somewhere in your notes, some kind of drawing like this, or just maybe an indication of, in your notes, atomic radius increases as you move down and to the left on the periodic table, then I would definitely put that in your notes. The reason is not because you're moving down and to the left, but because the electrons are being pulled. The electrons are being pulled less in the left bottom corner, and therefore can go out farther. than they are in the top right corner where the electrons are being pulled in very tightly. Okay? All right, last topic for today. We need to talk about valence electrons. Valence electrons, and we'll also kind of the valence shell. Okay, the valence electron slash the valence shell. Okay, valence means the electrons in the outermost shell of an element, of an atom, okay? The electrons in the outermost shell of an atom. So when we talk about the valence shell, we're talking about the farthest out shell of the electrons for an atom. And when we're talking about valence electrons, we're talking about the electrons in that shell, okay? So the atomic radius is the distance between the nucleus and the valence shell. All right? This is going to be unbelievably important for you to understand. Everything in chemistry is dictated by valence electrons. How things react with other things, why they want to react with other things, why they don't want to react with certain things. It all has to do with the valence electrons. Okay? Okay. So when we talk about this, and I want you to put this in all caps, we're going to make it a fun color because this is super important. Oh, that's not what I wanted. I want that, and then I want to make a new box that's even bigger because this is way important. And we want this to be red. And we got caps lock on. No, not yet. There it is. All atoms want to have a full valence. What the world? What is going on here? Nobody stopped me. I was like 6 words in. I want this to be like a presidential tweet.
That'd be a good presidential.
All atoms want to have. If the president of the United States understood this about chemistry, I would be, if he could demonstrate that he understood valence shells, I would be genuinely surprised and a little bit impressed.
A little bit. More surprised.
More surprised than impressed, but. Okay. All atoms want to have a full valence shell. Okay? Valence shells in all atoms, valence shells want to be full. Okay? There are 8 electrons all atoms want to have a full valence shell. There are 8 electrons in the valence shell. I'm going to put an asterisk on this
And you are still in that. Nothing wrong.
Want blue?
That's nice.
That's nice. There are a couple of exceptions, okay, but almost always there are 8. The primary exceptions are hydrogen and helium. But generally speaking, I'm going to change this color because it's hard to see. That's a little bit better. I wish that it would let me do like custom colors, but it won't. Hydrogen and helium are different. That's because they only have their first shell, which can only hold 2 electrons, but we'll talk about that later. Okay? There are 8 electrons in the valence shell. The other shells kind of vary in the number of electrons, but really what you need to know is that the electrons really want to have, or really, the atoms really, really want to have 8 electrons in their valence shell. And I'm going to show you a good way to remember how this works. Does anyone know the name that refers to all of these guys? Right? Oh, it's literally right there. The noble gases. Okay, the noble gases. And this is a way that one of my AP chemistry students referred to it, okay? All of the atoms want to cosplay as a noble gas. Okay, they all want to pretend that they are a noble gas. Noble gases all have full valence shells. Okay, so for instance, helium, well, helium has a full valence shell, but its valence shell only has 2 electrons. Okay, because the innermost shell of atoms only can hold 2 electrons. So for instance, you see this? It goes up by 8s. Okay, so 2 to 10 is 8, 10 to 18 is 8. Okay. This is more because we're adding another shell that has 16 in it. But krypton has a full valence shell, xenon has a full valence shell, and radon has a full valence shell. Everybody wants to be like these guys. Everybody wants to be these guys. Helium, neon, argon, krypton, and xenon and radon are called the noble gases because they're too cool for everybody else. Okay? They do not react with other elements. Really. The noble gases are unreactive. Everybody else does reactions because they really want to have a full valence shell. Okay? Fluorine is like, give me another electron. Like he's a crack addict who needs his electrons.
He's 1 away, too.
He's 1 away.
What a sad story.
He's literally 1 away. So he just wants that extra electron so bad. Okay? He wants that extra electron. And lithium over here is like, anybody want to take this extra electron? I got an extra electron here. Can somebody take it off my hands? Because lithium only has 1 electron in its valence shell. So what it wants to do is it wants to give it away so that it has just the shell beneath it, which is full. Okay? This is the reason for chemistry. Okay? This is the reason why things react. Has anyone heard of something called sodium chloride? Okay? You put it on your food all the time. It's table salt. Okay? Sodium, so if you look at your periodic tables, I want you to look in the top right corner of the square of sodium here in your periodic table. It will say 281. Do you see the 281 in the top right of the square in your periodic table? For sodium. These are the electron shells. It has 2, and then it has a shell with 8, and then it has a shell with 1. Now look at chlorine. 2, 8, 7. 2, 8, 7. Chlorine is really close, right? Really close to having 8 in its valence shell. And sodium has an extra electron. It has a full second shell. But then it has this one straggling electron that it just wants, like, can please somebody take this off my hands? I will pay you to take this electron off my hands.
I understand.
Because sodium, if sodium gets rid of that 1 in its valence shell, this becomes its valence shell. And it becomes very happy. So what happens with chlorine and sodium is chlorine and sodium make a deal. And chlorine says, I'll take that electron if I can have it. And chlorine says, please do. And so they bind together in what's called an ionic bond, and we'll talk about that later, where chlorine steals sodium's 1 electron. And then they both get to pretend that they're a noble gas.
Oh, that's weird.
Okay? Because and that's why it's stable. That's why salt doesn't like to react with other stuff. Salt just is happy the way that it is.
Except for slugs.
Except for slugs. That is true. Yeah. But do we see how that works? And the slug thing is actually more of a physical change than a chemical change. Yeah.
I still think it's so funny that it's sodium and chlorine.
Yeah. And here's the thing. Sodium and chlorine are so close to having full valence shells that they'll react with anybody. Okay? If you get pure chlorine gas, you will die. If you get pure sodium gas, probably also die. Well, pure sodium as a solid, but chlorine is like real bad. Okay.
Chlorine gas,
No bueno. Same with fluorine. Fluorine is scary. Okay. We brush our teeth with fluoride, which is a different thing. Fluoride means that it is bonded with something else, so it's happy. If you find fluorine toothpaste, don't buy it because it'll dissolve your teeth.
or maybe you.
Okay? If you find fluorine toothpaste, you need to take a step back and think, this is not a good idea. Okay? Fluoride means that it has bonded with something, and so it's safe. Okay? Oxygen. So we breathe in oxygen, right? But we don't breathe in just pure 1 oxygen atom by itself. It's actually 2 oxygen atoms bonded together. And the way they do that is they share a couple of electrons. So they get to pretend that they are a noble gas. It is called molecular oxygen. It is 2 oxygens bonded together. Valence shells, valence electrons. This is chemistry, all right? I need you to understand that. Yeah, Miguel.
So what I'm taking away from this, every single element is unstable, except when it's bonded with another element.
Well, okay, so it's not that it's unstable. Unstable suggests that it is radioactive. It is reactive. Most elements are reactive until they achieve a full valence shell. So it is very rare to find just pure sodium or pure lithium. Okay? Most of the time it has reacted with something. It's very difficult to find pure silicon. If you find pure silicon, silicon in the presence of oxygen binds together to make rock. Okay? silicon binds with oxygen, and so they get to pretend that they're noble gases. Yeah, silicon. So there's a lot to understand here, but this is the basic information that I want you to understand. Okay, that's going to finish up the majority of the lecture for today. I'm going to stop our video. Yeah. Okay.